We ended our last discussion by talking about a thin lens and went through a simple calculation that showed that with the thin lens approximation, for a lot of cases, or certainly in the first order region, the thin lens assumptions give us a solution that is reasonably accurate to define the properties of the system, but that doesn't really fully explain the power of the thin lens approach. Because in the paraxial region, what this thin lens approach allows us to do is we can take any lens, or in fact any two optical surfaces, and treat that as a thin lens. Okay? So let's say I had a couple of lenses in my system and I broke those down into thin lens approximations. I now have a pair of thin lenses, but I can now treat any of those two thin lenses as a single thin lens, and again reduce the complexity of my calculations significantly. So effectively, any optical system with any number of surfaces can fundamentally be treated for first order calculations as a single thin lens, and a thin lens is simply described by the power. The power of a component is simply the sum of the two surface powers. So if I want to do this, then the power of this thin lens is simply the sum of these two powers that were calculated applying this calculation to each of the previous optical components. So the power is simply the change in index times the first curvature plus the change in index times the second curvature. Change in index times the difference in the index times the difference in curvature. So it's easy to make the calculations, and then once you've made the calculations, you can define many of these paraxial or first order properties of your optical system. So let's now talk a little bit about how we define the imaging properties of an optical system. And I'm going to start by talking about something that's referred to as Gauss's imaging equations. And there are a few forms of imaging equations that are used. Gauss's form and Newton's form are probably the two most commonly used. But let's talk a little bit about Gauss's imaging equation. Okay? And again, we're going to use cardinal points that we just talked about, and this is that same figure we looked at previously, where I said that when a ray hits a surface in the paraxial region, the angle at which the light is propagating changes, but in an infinitesimally small region around the point of intersection, the height stays the same. As the light propagates through a medium of constant index, the height of the ray changes, but its angle stays the same. So what we can do is break our ray tracing down into one of these two relatively simple steps that we can apply either of our paraxial calculations, the angle change or the height change to, and again we can use the NU form, or we can use the reduced form, or the optical form of the angle and the height. Okay? So let's start with refraction. So the change in angle, NU minus N prime U prime, is equal to Y phi. Okay? And we can substitute based on our little sketch here. We can calculate U, again, sort of represents the sine of the angle, so let's just change that into Y divided by L, the height divided by the distance, and the same in image space over here. So we see that the power is simply minus N over L plus N prime over L prime. And again, this is taking into account, remember L in this case is negative because effectively in this case with our idealized lens, our principal points are located right here, and we're measuring this distance from our principal points, so this distance is negative. This distance would be positive because it's to the right of our reference point at the lens position. So how do we use these to calculate some of our optical properties, and what are some of the properties we're interested in? One is, of course, magnification. We start with an object that has a particular height, and we create an image of that object, and In this particular case, the object and the image height look to be about the same, but typically if I'm defining a photographic objective and I'm taking pictures of mountains that are thousands of meters high, obviously my image scale has to be a bit smaller. Lateral magnification is simply the ratio of the image height to the object height. So in terms of this little figure right here, my lateral magnification can be treated as h prime over h, but it also is equal to L prime over L. And these angles are going to be equal. Now there's also what's referred to as longitudinal magnification. And this is the magnification, if you will, for a thick object. Because if you think of something that has depth, the magnification of the side that is closest to the optical system will be different than the magnification of the face or the part that is furthest away from the optical system. So in this particular case I've got an object, and in this case I'm saying h1 is equal to h2, and the actual thickness is delta z. Okay? And I've got a distance z2 to h2 and z1 to the one that I've referred to as h1. So delta z is, again, this term right here. Remember, measuring from this point, that is a negative distance. That's why it looks like that. And the magnification of this object would simply be the ratio of its image height to its actual height. So it would look like this. And similarly, h2 would be its ratio to its image height. The actual longitudinal magnification would be the product of those magnifications. So the longitudinal magnification is approximately the square of the lateral magnification. So that's one of the optical properties we're interested. Another important concept is the aperture stop. Now, in this particular system, this is the Cook triplet, and again, you'll be seeing Cook triplet quite a few times this semester, including as our final exercise or our final example. But these little red tick marks right here represent the aperture stop of this system. Okay. Optical surfaces have a finite extent. Okay. There is going to be one surface in your system, and in some instances it may be lens optic itself or the mechanical mounting of the lens, or it may be a separate mechanical surface that limits the physical extent of the light that can make it through the system from an on-axis ray bundle. Okay. That surface is referred to as the aperture stop. So in this case, it is this mechanical structure that limits the size of the on-axis bundle that can make it through my system. So this is the aperture stop. Now, in a lot of photographic objectives, what you'll find is the aperture stop can be adjusted. It's a segmented or leafed metal structure that you can adjust to change the size of the stop, to adjust the amount of light that makes it through the system. But no matter what, there is one surface that limits the on-axis light bundle, and that's what we refer to as the aperture stop. The aperture stop is physically real. That's important, because often when we describe our optical systems or define our optical systems, when someone makes the specifications, typically what's specified is the entrance pupil. What the entrance pupil is the image of the aperture stop as seen through the object space optics. And the easiest way to think about this is, again, sort of a DSLR type camera where you can remove the lenses. If you take that optical system and hold it up to the light and you're looking at it through object space, you can see an image of that aperture stop. But because you're looking through optics typically, let's assume it's an embedded stop like in our Cook triplet, what you're actually seeing is not the stop itself, but the image of that stop. And that is the entrance pupil. the image of the aperture stop as seen through the object space optics. So the size will actually be different than the actual aperture stop, and the location will be different than the actual aperture stop. So the aperture stop is the physical surface, but it's the entrance pupil that is typically the first order properties of interest. Okay? Now if we think about the image of the aperture stop as seen from through the back end of the optics, the image spaced optics, that's what's referred to as the exit pupil. And the exit pupil is going to become more important when we talk about calculating wavefront aberrations, but just understand that we have an aperture stop and we can image it through our optical system to get either the entrance pupil or the exit pupil. And we will continue on with some of our discussion of first order optical properties in our next discussion. Thank you.